So we'll start.
This meeting is being recorded.
Okay. Will Klemens start and then you and then Kilian, or what is the order?
I think I will start and then Kilian and Ulrike will have the third part.
Okay.
Yes.
Okay. Thank you. Already 70.
This meeting is being recorded.
And first of all, I would like to welcome everybody and to say hello to all this audience, and a really warm welcome to this fifth seminar that is organized within the HITRIplus project. And today we are going to close the circle of the hadron therapy centers. And Marburg ion beam therapy centers will take the floor with the three talks that are aiming to illustrate and to introduce us this center. So we are glad to have an introduction of the center and of its activities by Professor Klemens Zink, who is the scientific and the technical director since August 2019. And then we will move to physics with Dr. Kilian Simon Baumann, who is a medical physicist at MIT and also a postdoc at the Radiotherapy department of the Marburg University. His research focus is in the investigation of lung modulation effects in particle therapy and track structure simulations of clinical particle beams. And then finally, we will also have a talk by Dr. Ulrike Schötz, who is head of the workgroup on molecular radiobiology at the Radiotherapy department of University of Marburg as well. She will speak about her activities that are related to hadron therapy, in particular radioresistance in head and neck tumors, and for which she investigates mechanisms and novel therapeutic concepts. So I'm really glad to leave the floor to our speakers. And please, Klemens.
Okay. Thank you very much for these nice words as an introduction. So my name is Klemens Zink, as Angelika already mentioned, and I'm happy for this invitation and for the opportunity to present our ion beam therapy center in Marburg. We are part of the HITRI consortium, and we are participating especially in the work package of radiobiology, especially Ulrike Schötz, and also in the work package of transnational access. So in Marburg, we offer the opportunity for patients to be treated here with carbon ions. Okay. I assume that not everyone knows where Marburg is within Germany. So you can see it here. It's in the mid of Hesse, about 80 kilometers north from Frankfurt and about 500 kilometers away from our capital, Berlin. The history of MIT is somewhat eventful, let's say. It's constructed by Siemens Healthineers, and there are two complete identical facilities in the world, one in Marburg and one in Shanghai. And start of the construction was in 2007, and the end of the construction in 2009. The installation of the accelerator started in 2008. And already in 2010, we had the first beam in the treatment room. And we were sure to treat the first patient in 2011. But then, because of some, let's say, financial trouble, there was a shutdown in 2011. And it took 4 years for a restart. So in 2015, the MIT started with patient treatments under the leadership of our friends from Heidelberg, HIT. And in 2019, there was a change in the ownership. The ownership went from Heidelberg, from HIT to, let's say, UKGM, so the University Medical Center in Giessen and Marburg. And so we are working at the end since 2.5 years here at Marburg. The technical equipment is very similar to Heidelberg, but we have no gantry, and also similar to Shanghai, as already mentioned, and Knau and Medaustron. So it's a synchrotron-based facility. We are able to accelerate protons up to 250 mega electron volts and carbon ions up to 430 MeV per U. And we treat the patients with active raster scanning. We have 3 treatment rooms with horizontal beams. You see here one of the treatment rooms and one treatment room with a 45-degree beam line. You see here the synchrotron and the ion source and the treatment room. The table is robotic based, and we have a KV imager in the treatment room, able to perform orthogonal KV images for the positioning of the patients. We have no in-room CT. The patient statistic, so we treat about 27 patients per month, let's say. You see here the statistics, maximum 37 patients beginning last year. And I assume due to Corona, the numbers of our patients decreased this year. The total number of all patients here in 2018, we started with 250 patients. 2019, nearly 300 patients. In 2020, we had 23 patients, and last year, due to Corona, there was no increase, but a small decrease in the patient numbers. So we had 311 patients. From all these patients, about 60% were treated with protons, and about 40% were treated with carbon ions. And the treatments, about 66% of, so let's say 2/3 of all patients were treated with primary therapy, and about 1/3 has been a boost treatment. Since the opening in 2015, we treated more than 1,600 patients. And I think at the moment we are in the range of 1,700, more or less. Okay. The tumor entities we treat here in Marburg, you see the statistics. About 40% of all patients had a CNS tumor, with the more differentiated here on the image on the right: gliomas, meningiomas, chordomas, chondrosarcomas, and several irradiations of glioma, meningioma, and so on. And we treat about 7 to 8% children, pediatric tumors, also CNS tumors, but also sarcoma, and our largest planning target volume we treat here at Marburg is the neuroaxis with protons, or for children, and let's say young people up to a length of about 160 centimeter, about, more or less. Okay, we initiated during the last, let's say, 2 years, also clinical trials here at MIT. Most of those, 3 of them are clinical trials for glioblastoma. That's a GIRUS trial and the König trial, and also a phase 3 clinical trial, also grade 2 and grade 3 glioma. Okay, and then a registry trial, also already recruiting patients. The research at MIT is open for radiobiology, for medical physics, and for particle physics. And since 2018, the MIT hosted about 18 scientific projects and scientific groups performing experiments here at MIT. And we have annual grants for beam time, not for all groups, but only for Hessian research groups. And I think about some of these projects performed by our group will talk now Kilian Baumann from medical physics, and afterwards Ulrike Schötz will present some radiobiology projects here performed at MIT. So I assume that we will answer all the questions at the end of this talk. And so I will hand over to Ulrike. Ulrike, you can start with your presentation.
Sorry, but I thought Kilian will be the next one.
Oh, sorry.
I will go for the second part.
Yeah.
Okay, so can you see my slides?
Yes.
Yeah.
Perfect. Okay, thank you, Clemens, and thank you, Angelica, for the invitation. And also from me, a warm welcome to today's seminar. My name is Kilian Baumann. I'm a postdoctoral researcher at the Philipps-University of Marburg and a medical physicist at the MIT. And I will present the most important research topics that we are working on. And the first research topic is the particle therapy of lung cancer patients, where we face 2 major challenges. That is, on the one hand, the investigation of lung modulation effects, so the effect of the heterogeneous lung tissue on the dose distribution. And we have developed a treatment planning optimization module to account for these effects. And the second challenge is, of course, the breathing-induced motion of the target, where we have developed a so-called 3D range modulator that enables an irradiation under breath hold. The second main research topic is the Monte Carlo-based dosimetry, both on microscopic and macroscopic scales. So for the macroscopic scales, we have calculated FQ and KQ factors for air-filled ionization chambers. And for microscopic scales, we are using the Monte Carlo coaching on 4DNA to calculate track structure simulations on cellular scales. And another more practical topic is the optical range verification. This optical range verification is a quite easy approach for the clinical quality assurance of energy-intense range of the particles. The setup itself is quite simple. We use a water tank that is irradiated here from the left with protons or carbon ions. And we use a CMOS-based camera to just collect the light that is emitted by protons. And here, 3 exemplary light distributions for protons of several energies are shown. And as you can see here, the Bragg peak is clearly distinguishable. And we can use this method to determine the range of protons and carbon ions on the sub-millimeter scales. We have already verified this optical range verification tool against well-established approaches like the PTW Bragg peak chamber or the IBA giraffe, and we found very good agreement between the different measurement systems. And using this optical range verification, we enable a detection of changes in the energy of roughly 0.5 MeV. The main question that remains, however, is that the source of light is not that clear. Of course, in the entrance region, the energy of secondary electrons is high enough to produce Cherenkov radiation. However, at larger depth, especially the depth of the Bragg peak itself, the energy of secondary electrons is not high enough to produce Cherenkov radiation. Hence, the source of light must be a different source. And currently, we are performing measurements of the spectral fluence of the light to identify where this light really originates from. For the Monte Carlo-based dosimetry on microscopic scales, we are using the Monte Carlo code GEO4DNA. And this codes enable to simulate track structures on the nanometer scale. And you can use the code to calculate energy and dose depositions down to several electron volts. Furthermore, the code enables the modeling of the DNA and complete cell structures and geometries. And we are mainly using the code to calculate the quality and quantity of DNA damages for different radiation quantities in proton and carbon ion beams. And we are using the code to investigate the flash irradiation effect. For example, we use the code to investigate the production of chemical radicals as a function of the beam intensity. And in general, on the long term, we want to use this code to develop a tool to support our cell experiments. And of course, the overall goal is the optimization of RBE models, both for protons as well as carbon ions. For the Monte Carlo-based dosimetry on macroscopic scales, we were part of the RT-norm project within the update of the TRS 398 code of practice. And we used the Monte Carlo codes Fluker and GEO4 to model air-filled ionization chambers and to calculate FQ and KQ factors as a function of initial proton energy. And here for some exemplary ionization chambers, the FQ factors are shown as a function of initial energy. And here all the data values that are currently available in the literature are shown. And mainly 3 Monte Carlo codes have been used. This is Fluker, GEO4, and PEN-H. And as you can see, for low and medium energies, we have a quite good agreement between the different Monte Carlo codes, so an agreement on the 1% level. However, for higher energies, we have larger differences between the different Monte Carlo codes, and we have differences of up to 3%. And we assume that the difference between the Monte Carlo codes for high energies is a result of different modeling approaches of nuclear interactions, whereas the role of nuclear interactions increases with energy. So differences in the modeling of nuclear interactions are not that important or have not such a large impact for low and medium energies. However, for high energies, where we then can observe these differences of the Monte Carlo codes. And currently, we are investigating the role of nuclear interaction models. We are using the different codes to identify the nuclear interactions that are responsible for these differences, and then want to measure these nuclear interaction cross-sections to find which of these values is the most accurate. So coming to the particle therapy of thoracic tumors, the big advantage of particle therapy, of course, is that we can apply a high and homogeneous dose to the target, whereas we can spare the surrounding healthy tissue significantly better compared to photon-based radiotherapy. And especially, we can significantly better spare the normal lung tissue and organs at risk, like, for example, the heart or esophagus or spinal cord. And especially the dose deposited to normal tissue in photon-based radiotherapy is a limiting factor for applying a high dose to the target volume. And since we have a smaller dose deposition with particles, we are able to use a dose escalation approach to cure our patients. However, of course, we have challenges that we have to overcome when treating thoracic tumors with particle therapy. And the first challenge, of course, is motion. So due to the breathing of the patient, the target volume itself is moving. And our solution is a so-called 3D range modulator that enables an irradiation under breath hold. And when irradiating under breath hold, we can nearly eliminate breathing-related motion artifacts. The second challenge is the so-called lung modulation effect. Here, the heterogeneous structure of the lung tissue leads to a distortion of the dose distribution. And we developed a treatment planning optimization module that can account for these effects. And the origin of the lung modulation effects is the heterogeneous structure of the human lung tissue, where we have structures with sizes in the order of some 100 micrometers. And this heterogeneous structure leads to a distortion of the Bragg peak. As you can see here in purple, an unperturbed reference proton depth of distribution is shown after traversing homogeneous materials. And in green, the same protons after traversing lung tissue. And as you can see, the Bragg peak is a lot broader, and of course, we have a larger distal fall-off. And now when treating a complete tumor volume, we then have, due to the lung modulation effects, an underdosage on the target, as here at the proximal end, and especially at the distal end. And this underdosage can clearly be visible here in the dose volume histogram. The main problem now is that this fine structure of the lung tissue is not sufficiently resolved in clinical treatment planning CTs. And in the clinical treatment planning CTs, the lung tissue is predicted to be more homogeneous. So when we are planning our treatment plans of such a CT image, our treatment planning system will predict a dose distribution as shown here in purple. And the prediction is a homogeneous dose deposition in the target volume. However, then in the patient, due to the lung tissue, we have a dose distribution more like the green curve here, and we have this resulting underdosage of the target, which negatively influences the particle therapy outcome. So in the recent years, we developed a mathematical model to describe this degradation of the Bragg peak. Starting from an unperturbed reference curve, we can estimate the degraded dose distribution by convolving the reference curve with the normal distribution. And from the parameters, so the mean value and the width of this normal distribution, we can then derive a newly defined material parameter, the so-called modulation power. And this modulation power is a quantity that estimates the strength of the modulation effect. And this modulation power can be measured in in-beam experiments using porcine lung tissue. And in a previous study, we used this porcine lung as shown here and deposited it downstream from our nozzle and measured then dose distribution behind the lung tissue. And then from optimizing this convolution, we were then able to derive modulation powers. The problem, however, is that the modulation powers measured with these porcine lung tissue is not really applicable to human lung tissue, because on the one hand, the structure size of the lung tissue in human lung tissue might be different compared to porcine lung tissue. And on the other hand, due to the preparation of the lung tissue samples, we mechanically influence the structure of the lung tissue and hence influence the outcome of the modulation power. So we developed a second approach, and this approach is based on clinical CT images. So although the structure of the lung tissue is not resolved in the CT images, we can estimate or derive the modulation power by performing a histogram analysis of the Hounsfield units and by investigating the distribution of Hounsfield units in combination with a certain calibration of our CT image. We are able to reproduce the modulation power on the basis of clinical CT images. And the greatest advantage of this approach is that we are able to estimate the modulation power both position resolved within the lung and especially for each patient individually. And based on the concept of the modulation power, we developed a Monte Carlo-based solution to reproduce lung modulation effects on clinical CT images. So in the patient, in the lung tissue, we have a binary density distribution with a very heterogeneous and fine structure, and these structures are not depicted in CT images. In the CT image, we have to deal with rougher structures, namely the CT voxels with an edge length in the order of 1 millimeter. And to reproduce the lung modulation effects, we are just performing a modulation of the mass density of the voxels within the lung. And by modulating the mass density, we are able to reproduce the lung modulation effects. And the function, the probability function we need for modulation of the mass density, we can directly derive from the modulation power. And using this concept, we investigated treatment plans for several lung cancer patients. and optimized these treatment plans without consideration of lung modulation effects, and then recalculated the dose distribution with consideration of lung modulation effects. And then by comparing both dose distributions, we are able to extract the modulation effects. So here, the effect on the high dose region is shown with the exemplary 90% isodose line. In purple, we have the prediction of the 90% isodose line given from the treatment planning system. And in green, we have the 90% isodose line as it would be in the patient due to the lung modulation effect. In white here, the planning target volume is shown. And as you can see, in the patient, the high dose region is quite smaller compared to the prediction from the treatment planning system. And we have range uncertainties of up to 10 millimeters. And similar effect can be seen for the low dose region, here depicted by the 20% isodose line, where the lung modulation effects lead to a small overshoot of the low dose region in the modulated case. And we have range uncertainties of up to 5 millimeters. Concerning the dose uncertainties in terms of the average dose in the CTV, we found that for proton irradiation, uncertainties can, the underdosage can be of up to 5%. However, the effects are more pronounced for carbon ions, since the Bragg peak of carbon ions is much sharper than protons. And in the last step, we then developed a treatment planning module that accounts for lung modulation effects. So again, we started with an optimization of the treatment plan without consideration of lung modulation effects, shown here in black. And then in green, again, the resulting dose distribution as it would be in the patient, with the underdosage here clearly detectable in the dose volume histogram. And then when we are using our treatment planning module, we are degrading our base data set. So we are taking the dose distribution from the base data and degrade them by convolving them with normal distributions. And when optimizing the treatment plan with these degraded dose distribution, we can account for lung modulation effects. And the optimized treatment plan then is here shown in the red curve. And as you can see with our module, we can recover the dose coverage in our treatment planning volume. And using this treatment planning module, we are able to reduce dose uncertainties due to the lung modulation effects to below 0.5%. And of course, we intensely tested and verified our treatment module with in-beam experiments. So coming to the second challenge in particle therapy of lung tumors is, of course, motion. So due to the breathing of the patient, the tumor volume is moving. And we have a second movement, and that is when we're using the active scanning technique for beam application, we have a movement of the beam. And then, of course, we have an interference between the movement of the tumor and the movement of the beam. And as a result, we have so-called interplay effects. And these interplay effects lead to a heterogeneous dose distribution with so-called hot and cold spots. And this heterogeneous dose distribution, of course, negatively influences the therapy outcome. So our approach is, or the question is, can we achieve a sufficient reduction in irradiation time to enable an irradiation under breath hold? And to be able to understand where this long irradiation times originates from, we have to look at our beam application system, the so-called active scanning technique. In the active scanning, the tumor is divided into several layers. And to reach a specific layer, we accelerate particles to a certain energy. And then this layer is dose painted in 2 dimensions. And then a different energy of particles is accelerated to reach a different layer in the tumor. And then again, the dose painting starts. And the problem is that we have to accelerate particles to different energies. And this acceleration takes time in the order of seconds. And hence here for an exemplary treatment plan with 16 energy layers, we see that we have a complete irradiation time of roughly 80 seconds due to the spill pauses that we need to accelerate particles. So the question is, or the approach is, can we enlarge the Bragg peak of a monoenergetic particle to have a spread out Bragg peak so that we can irradiate the tumor in the complete depth with only using one energy of the particles? And our solution is the so-called range modulator. This range modulator is similar to a ripple filter and consists of this pin-like structure. And particles now traversing this range modulator will experience different amounts of material depending on the position where they traverse the range modulator. And due to this different amount of material, we have different energy losses resulting in variable ranges. And hence, using the spin-like structure, we are able to apply a spread out break peak by using just one single energy. And by altering the height of the pins, we can directly influence the width of our spread out break peak. So in general, this structure enables the irradiation or the application of a spread out break peak with only one energy. And of course, we can then arrange pins of a different height at different positions and hence can enable a dose distribution in 3 dimensions for any 3D shape we want to irradiate. And the principal procedure is that the shape of the range modulator is optimized in Monte Carlo simulations. And then we can easily 3D print our range modulator in a 3D printer made from plastics. And then, of course, we perform a quality assurance where we measure the dose distribution downstream from the range modulator and compare it with the simulation. And on a clinical scale of dose uncertainties, we can perfectly achieve the dose distribution that we predicted in our Monte Carlo simulations. And of course, we can use the 3D range modulator for complex tumor geometries and especially for patient individual tumor shapes. So starting from the CT image of a patient, we can for each beam directly extract the shape of the tumor volume. And then using our Monte Carlo simulation, we can then optimize the design of 3D range modulator and subsequently can easily 3D print it. And in this case, of course, we also performed the quality assurance. And again, the measurements show that the dose distribution achieved with the range modulator is on a clinical scale exactly the one that we predict in our Monte Carlo simulations. Though the 3D range modulator leads to a significant reduction in treatment time, so here for our exemplary treatment plan, where we needed roughly 80 seconds for the conventional active scanning method, we can reduce the irradiation time to under 5 seconds. So the range modulator can apply a dose conformity comparable to pencil beam scanning. However, we only need one single energy and hence treatment time is only in the order of seconds. And in the order of seconds, of course, an irradiation under breath hold is possible. And this enables an almost elimination of motion artifacts. And a second application for the range modulator is flash irradiation. And in flash irradiation, we want to apply a high dose in a very short time. And with the active scanning method and a slow energy selection, and flash irradiation is not possible. However, when using the 3D range modulator, we only need one energy, so we do not have the slow energy selection, and hence can enable flash irradiation. And so the range modulator is also essential for the flash irradiation. And with that, I'd like to thank you for your attention and give the word to Ulrike for the radiobiology part. Thank you.
Thank you, Kilian. I am happy to be here today and be able to show you the research which is going on in our radiobiological lab in Marburg. So the lab in Marburg has a focus on the tumor entities head and neck squamous cell carcinoma and on non-small cell lung cancer. Both are well known for their resistance towards radiotherapy and for a frequent local relapse. In our preclinical studies, we saw examine mechanisms that lead to this strong radioresistance and also develop like targeting strategies to radio sensitize these tumor cells. We also do screen for biomarkers, which can help in identifying such radioresistant cases. And then we study them functionally for improved therapies. I mean, we do this for both photon and particle irradiation. The response of HNSCC towards radiotherapy is mainly defined by an inherent and an acquired mechanism of radioresistance, and especially HPV infection and variations in the DNA damage response. After irradiation with photons or carbon ions, one of the most prevalent mechanisms is actually senescence, and it's accompanied by the secretion of factors into the tumor microenvironment, which trigger inflammation and also support survival and relapse of the tumor. Mechanisms of DNA repair are a very strong determinant of the therapy success, and they vary considerably in the head and neck squamous cell carcinoma, specifically depending on HPV infection. So in this regard, we study several factors which are involved in some signaling pathways responsible for both senescence and DNA repair. We specifically look for CXCR2 signaling, we look for kinase signaling, and we look especially for replication-associated DNA repair. On the other hand, we have the NSCLC, and they exhibit quite a large variation of mutations in signaling pathways that are involved in cellular survival, invasion, metastasis, and in this case, especially hypoxemia and pulmonary infection play a major role in the disease. We identified some factors in the signaling pathways, such as HIF or SCFC-KIT, which become elevated after photon, but not after carbon ion irradiation, showing the advantage of this therapy. And yeah, so this is basically in general what our lab does. And in the following, I would like to show you more details about one of our ongoing projects. It's in HNSCC, where we elucidate the differences between HPV positive and HPV negative HNSCC and the consequences for carbon ion therapy outcome. And we do this in a preclinical study, obviously. So HNSCC is actually the sixth most prominent tumor disease in men, and it ranges on position 15 for female cancer. It can be distinguished in the two sub-entities of HPV positive and HPV negative, where HPV negative mostly originate from kind of lifestyle risk factors such as smoking and alcohol, and HPV positive developed due to a viral infection with the high-risk human papilloma virus. Whereas HPV negative can occur in any location from larynx to oral cavity, the HPV positive are actually restricted to the oropharynx. In high-income countries, HPV positive HNSCC is actually on the rise. When like 20 years ago, they accounted for around 10 to 15% of HNSCC, nowadays is more around 30% or even higher. Even though the HPV positive and the HPV negative cases are considered to be like different sub-entities, since carcinogenesis is completely different, and also treatment outcome, as I will show you in the next slide, varies significantly. But anyway, both receive the same treatment options. The treatment includes surgery, it includes radiotherapy with quite high doses, and it includes a concomitant chemotherapy. Histopathologically, the detection of the P16 status will be done, and together with the tumor location, it is used as surrogate marker for identification of an, sorry, something's going on with my laser pointer. Yeah, so it is a surrogate marker for the identification of an HPV infection. It is used as a prognostic marker, but it does actually have no influence on the therapy decision making, really. This study now shows you the current treatment outcomes of a German patient cohort, which is treated with radiochemotherapy. The patients were stratified according to their HPV status in HPV positive and HPV negative cases. Local regional control is good in HPV positive, but HPV negative patients relapse in 20% of cases. And this has a direct impact on overall survival as well. It is like 80% for HPV positive, but only like 60% for HPV negative, given a time period of 5 years. So even though there was an impressive progression going on actually in the therapeutic strategies over the past years, the results are still moderate and calling for an optimization of the therapy. However, standard therapy can not be further extended. I mean, maximum doses of photon therapy are reached already, and the quite intense regimen causes high normal tissue complications. Even though alternative treatments were looked for, such as EGFR inhibition with cetuximab, these concepts proved to be not superior to the standard therapy. So there's actually a strong need for an improvement of the therapy on the one side, but also for reducing the strong side effects and improving quality of life of the patient. And this brings carbon ion irradiation into the focus, since it enables more cell killing without increasing the dose due to the higher relative biological effectiveness, with simultaneous reduction of the side effects due to the higher conformity of carbon ion beam application. Like up to now, the clinical studies of irradiating head and neck cancers with carbon ions, they do not really distinguish between HPV positive and HPV negative subentities. So with our preclinical study, we aim to clarify how the two entities behave towards particle therapy, and we compare them with photon therapy. It was shown by our lab and by other labs as well that in vitro HPV positive HNSCC cells exhibit a higher sensitivity towards photon irradiation than HPV negative do. This is visible in the left graph here, where a colony formation assay was performed on one HPV negative and one HPV positive cell line. And the HPV negative cell line exhibits a significantly higher radioresistance. Given a whole set of cell lines, as shown in the graph on the right side, demonstrates a significant difference in radioresistance between the two entities, and hence is in agreement with the tumor patient data. If you irradiate now the same set of cell lines with carbon ions, first of all, it leads to an expected result. So both entities are more sensitive to carbon ions than to photons. However, the RBE, the relative biological effect, is higher for HPV negative with 2.8 than for their HPV positive cells with here 2.2. Interestingly, so the difference in radio resistance, which we could observe after photon irradiation, is decreased after carbon ion irradiation, and the significance is lost. We in the next step also observed the DNA double-strand break repair after carbon ion irradiation by examining gamma H2AX and 53BP1 foci, as you can see here in the pictures. And they account as markers for radiation sensitivity. So the more residual foci we can observe 24 hours after irradiation, the more sensitive the cell line reacts. After photons, there is a significant difference in the amount of residual foci between HPV positive and HPV negative, confirming the higher radiosensitivity of the HPV positive cells. However, the significance is lost after carbon ion irradiation. So there is no difference, not for irradiation with the isoeffective dose and not for irradiation with the isophysical dose. So this difference in radiosensitivity, which can be observed for photon irradiation and which is made responsible for better treatment outcome in HPV positive patients, becomes lost after carbon ion irradiation. And how can this be explained? So to understand this, it's important to know that HPV positive cells harbor a defect in the DNA repair mechanism of homologous recombination. After photon irradiation, homologous recombination and non-homologous end joining are the two major repair pathways which become activated. An alternative mechanism to homologous recombination would also be alternative end joining, which is known to be active in tumors which harbor a defect in a homologous recombination. In HPV positive cells, the recruitment of the DNA repair protein RAD51 is not fully functional. But this protein is really essential to the process of homologous recombination. It is recruited to a maximum approximately 4 hours after irradiation, and it will disappear again after repair is completed. This is actually what happens in HPV negative cells, but not in HPV positive cells. So observation of the protein recruitment over a time period of 10 hours after irradiation shows that the active recruitment and repair is only performed in the HPV negative case. And the same can be confirmed for a whole bunch of cell lines, and the result is significant. So our group identified that homologous recombination is not a dominant pathway which is used in HPV positive cells. We also found out that non-homologous end joining is still active. And other groups made the valuable observation that HPV positive cells shift their repair mechanism from homologous recombination to alternative end joining. So for DNA repair after carbon ion irradiation, things still remain quite unclear. And the dominant repair pathway actually is not yet really identified. However, we know from publication of others that after carbon ion irradiation, cells tend to aggregate end resection by the enzyme HITRIplus, which would suggest that a repair of those lesions is done by alternative end joining. Bringing all the information together, we suggest that for the case of HPV positive cells, the lesions caused by carbon ion irradiation will be repaired predominantly by alternative end joining. And this will explain also the observed survival advantage of these cells after carbon ion irradiation. Okay, so in conclusion, I would like to say that the impact of homologous recombination and repair of carbon ion induced lesions is low in HNSCC cells. And while HPV positive cells are significantly more radiosensitive to photons than the HPV negative cells, no significant difference was seen after carbon ion irradiation. And this, we think, is actually something that needs to be considered when planning new treatment protocols for the treatment of HPV positive tumors with carbon ions. At the moment, the lab proceeds with further carbon ion irradiations experiments. So we really want to prove that everything is valid with this hypothesis. So what we do, we characterize at the moment further the homologous recombination via Rad51 after carbon ion irradiation. We do knockdown experiments, and we also go further into early and functionally examine the replication associated homologous recombination, and we also examine the alternative end joining capacity after carbon ion irradiation. So with this, I'm coming to the end now, and I say thank you very much for your attention. I also would like to show you all people who are involved into the physical and into the biological research, into the clinical studies, the physicians, the physicists, and the biologists. So thank you very much. And Klemens, Kilian, and I are happy to take your questions.
Thank you. Thank you very much, Ulrike and Klemens and Kilian. Very, very nice and interesting presentations. Now we have. Sorry?
Maybe I can make two remarks, especially
Yes,
concerning
please.
the contributors, and especially for the range modulator Kilian talked about. We have to thank, and there's a strong collaboration with the biophysics group from GSI. And so we work strongly together with especially Uli Weber and Christoph Schui, so that I have to remark. And maybe the next regarding this 3D modulator, we performed last year our first, to my opinion, it's the first experiment where we indeed applied flash dose rates in a, let's say, macroscopic planning target volume of several cubic centimeters, and not at our facility, but at the facility in Denmark. And so we assume that we will be able to perform indeed flash treatments with 3D modulators within this year. Yeah, that's the two remarks. Okay.
Okay, thank you. Thank you very much, Klemens. And just before I start with the question, I would like to ask you to turn on your camera, if you want, of course, so that Petya will be able to take the usual picture of our seminars. So just please a few seconds, let Petya to do it, and smile. And just Petya will let us know when she has done it.
Yes, just waiting for everybody. Okay.
Okay, thank you. Thank you very much, Petya. And in the meanwhile, we have a question from Markus Hager. I guess it's for Kilian or for Klemens. And he asked, the MIT accelerator uses an RF exciter for extraction of the beam. Other centers are using different extraction methods. I'm wondering, do you see any particular advantages or disadvantages of the KO excitation, especially as you are now using less beams to produce the spread out bright peak?
Indeed, we use an RF exciter. And so, do you see any particular advantages, disadvantages of the KO excitation? Also to clarify or to make it clear, at the moment we do not use these modulators for treating patients. We do not use less beams to produce SOBP. We have conventional ripple filter at this time, and our slice thicknesses for carbon ions is about 3 millimeter. Yeah. At the moment we are not using this technique here at Marburg. And because I see the next question, we will never be able with our synchrotron to perform flash treatments. But we have a strong collaboration with Varian, and they plan clinical trials with flash at some of their facilities, especially in Holland and Delft. They plan it, and our experiments, indeed, for these flash experiments we are performing in Delft, yeah, not in Marburg. I'm sorry for that, but that's the way. Marcus, is your question answered?
Yeah, you answered it. Thank you. You're not actually using it. I mean, I guess I was wondering, the excitation method, of course, influences the time structure of the beam and the intensity you see, and especially for flash or with your 3D filters, you might see these effects in the dose distribution then. Here
in Marburg, we will not be able to perform these flash experiments. Yeah. Maybe in very, very, very small fields, maybe, but never for clinical applications. Yeah.
Yeah. Thank you.
Yeah, so you have already answered to the question from Marius. Are you planning to do clinical trials with flash? So you
no, not here in Marburg, but maybe in collaboration with Varian. It's now a Siemens company, maybe, but we are working on the technique to prepare flash treatments within the SOBP at Varian machines. Yeah.
So the limitation is basically the intensity that you can have in the synchrotron.
Yeah. You're right.
And this comes from what? Injection process or?
So I'm not a real accelerator specialist, but to what I know is that all the exciting is too slow, and it's for all synchrotron-based facilities, they will have a problem. At the Varian machine or at cyclotron-based facilities, they are able to get a beam current of about 800 nanoamps, and that will be enough for flash, but only for the highest energy, for the 250 MeV, so for protons. And I assume that, or I'm sure that flash experiments or flash patient treatments will be performed at cyclotron-based facilities. Yeah. I assume, or no, I know that in Heidelberg at HIT, they have optimized their synchrotron, and they have performed experiments within field sizes of 1 by 1 square centimeter to reach dose rates in the range of 40 gray per second. Yeah, but only for this very, very small field size. Yeah. And maybe if you optimize our synchrotron, we will also be able, but it's not the main focus here, yeah, to perform these experiments here in Marburg. We performed all the experiments and the development of these 3D range modulators, but for especially for these movements, moving targets, but for flash experiments, we will collaborate with Varian. Okay.
All right. Thank you very much.
Yes, we have another physics question from Alexander from Medostron. What is the disadvantage of the range modulator with respect to standard treatment? Why is it not considered for not moving target volumes?
You can consider it and it will work. And you can accelerate your treatments. Yeah, that's always fine. And maybe it would work within several years, but first of all, we have to establish all the workflow. Yeah. So I think it will take, let's say, 2 years, 3 years to include it in this medical equipment. Yeah. So in summary, it's possible. You will spend less time for the treatments, so it's good for the patient. But all these engineering questions and so they are not still at the end.
Klemens, may I add a comment to that?
Yeah.
I think you also need to consider that this 3D ripple filter is then really a field or portal specific, and you have to exchange it between the portals and the fields and the patients. So it's a balance between the savings and additional effort on the other side.
Thanks, Peter, for this comment.
Okay, now we go to the biology, so to Ulrike. The HR repair seems to play a minor role for carbon irradiation of head and neck small HNSCC cancers. Was this expected?
Well, I would say yes and no, both at the same time. So there are many publications and many groups who made experiments about this. So there are some groups which say yes, it plays a role, and other groups which say it does not play such a big role. It's more the non-homologous end joining. But after all, I think it's now really necessary to talk also about alternative repair pathways, which were not really examined yet so extensively. Yeah. I think it would be quite interesting to know whether we really have this switch to the alternative end joining. So if HR plays a role or not, it's also very difficult to say because it is a complex mechanism. Yeah. It depends on in which phase of the cell cycle the cell is, and it also depends on the chromatin remodeling which is taking place. So it's not really a yes or no question. Yeah, so it can be dependent on many factors. But we think in the case of HNSCC specifically, it plays definitely a minor importance.
Okay, thank you, Ulrike. Do we have any other question? No, it seems no. And again, I really thanks the speakers and all the people that attends the meeting. And on behalf of the Work Package 2, I'm also glad to anticipate that the next seminar will be held in the second half of March, and by Dr. Insa Schroeder from GSI. And she will talk about the use of organoids in hadron therapy studies as a model to study the effectiveness and toxicity of this treatment. So just stay tuned and we will tell you the exact data. I would also like to thank Manjit, Petya, and all people from our networking and communication work package for organizing these seminars. And I just leave you with wishing you a nice evening. And
Angelica, may I say something?
Yes, sure, Manjit.
So while we have most of, oh, this is strange. Can you still get feedback? Okay.
Yes.
Okay, so I was just going to say, we are always looking for interesting series for our monthly seminars. So if anybody is interested in trying to present something new or exciting that they would like, please send us a message. Now that we have covered all the 4 hadron therapy centers where we wanted to make that a priority because of the beam access that is available for you to be able to collaborate and do your research. So once again, I urge you to look at our HITRIplus website and submit proposals for beam access, because that's one of the nice things about infrastructure projects funded by the EU, that's available. And secondly, if any of you are interested in giving a seminar, please send a message. I see lots of old and long-term colleagues online. And if you don't volunteer, I will probably send you a message. But of course, if you'd like to, that's even better. So thank you very much. Thanks, Angelica. Sorry, go ahead.
Thank you. Thank you very much for reminding us about these opportunities. So have a nice evening and see you next time.
Great.
Thank you
again.
Thank
Bye.
you. Bye.
Bye. Bye.
Thanks very much.
Bye.